Hi, everyone. Welcome back. So just a quick one today, really to cover off a pretty important, but often kind of just shrugged aside topic when we're talking about organic reactions. And that's the idea of functional groups and polarity. So we've seen this a lot already. As we've gone through the different functional groups, we've called some polar, some non-polar, how it's affecting polarity. But haven't really clarified that since the fall, and how the functional groups are going to modify the polarity of organic molecules is a completely new topic. So just remember when we're talking about polarity, what we're saying is a molecule that has a pretty high dipole moment. So something that has a strong difference in electronegativity between one of the atoms and another that isn't balanced out, right? So here the chlorine has quite a large electronegativity, so we're going to have a slightly negative charge over here. And that means the hydrogen is going to be a little bit positively charged, right? Most of the electronic density is going to be pushed onto that chlorine. If we look at something a little bit larger, so let's look at, we should remember this molecule now, so that we're going to call this, just to practice the naming, it'll be a cis dichloroethene, right? And it's got its two high electronegativity atoms on the same side of this bond. So this side is generally going to be a little bit negatively charged. This side will be a little bit positively charged. So we're going to have a dipole moment on this thing. There's going to be a polar molecule. However, if we look at the trans variation, okay, here, so this is the trans dichloroethene. Now, each of those dipole moments are canceled out all the way around the molecule. So this is a nonpolar molecule. Okay, so when we think about, say, something like the physical state or the boiling point, or how we would expect this to behave in different, let's get rid of those arrows. Here we go. Scenarios, okay? So with the trans isomer, there's no dipole moment. So really, these molecules aren't going to interact very strongly with each other. As opposed to, say, the cis variation, the cis isomer. Now, if we stack another one up, so its negatively charged dipole moment will be attracted to another molecule's positively charged side. So these are going to have a higher boiling point. It's going to take more energy to pull those molecules apart than something that doesn't have that dipole moment. Okay, so why do we care in terms of organic molecules and organic reactions? We have to think about what kind of solvents we're doing these reactions in. So water as a molecule, if we look at it, so we've got oxygen with two lone pairs. So this is at a very high electronegativity on the oxygen. So this whole side is going to be a negative side, and we'll have a positive side on the water molecule. So each of those hydrogens are going to be a little bit positively charged. And that means that the lone pairs on the oxygen are going to be attracted to those hydrogens on a neighboring water. So that's where we generate a hydrogen bond. And it's the hydrogen bonds that make the surface tension in water that make it possible for our lungs to operate correctly, or for the weird Jesus lizards to go running across the water surface. It's why water is such a small molecule, but it's still liquid at room temperature and takes up to 100 degrees to turn it into a gas phase. Anything else like this, say ammonia, is going to have a much higher pressure on it. Or say like something that's along the same molecular weight. Nothing's coming to me right now, but say hydrogen cyanide, for example, is even heavier than that. So that's HCN. But this also produces a gas at room temperature. Okay, so it's that hydrogen bonds and the polarity of the molecule that's giving it all of its properties. So when we're thinking about the properties of organic molecules now, the polarity of the functional groups that we stick onto it is going to really determine whether or not it's soluble in water or polar solvents, even including ethanol, ketones, DMSO, so that's dimethyl sulfoxide, is going to depend. So if we start with something that is just a carbon chain, there's no dipole moment here, so water's going to have a hard time forming a network or a complex around it. We'll talk about nonpolar solvents in a minute. But if we start hanging off, say, alcohol groups, even an amine, because the nitrogen can also participate in hydrogen bonding. Definitely if we give it some carboxylic acid groups. This now has lots of opportunities for water to interact with it, right? So there's our water. Now we can form some hydrogen bonds, and the water can actually form a complex around this molecule in a way that allows its network to stay intact. So this would be a polar molecule that's going to be relatively soluble in polar solvents. But what if we stick with that just regular carbon backbone that doesn't have any polarity to it? Now we'd need to switch to something like, say, a benzene or just a hexane. Okay, we'll do the benzene here. Hexane, 1, 2, 3, 4, 5, 6, right? Carbon tetrachloride, so that's CCl4, quite toxic. So none of these have a dipole moment, so they don't really care if the molecule that's interacting with it has a dipole moment either. It's not going to, you're not breaking up any network, anything like that. So if we have a phase, let's say a separation funnel, okay? So something that's going to look like something like that, where we'll have a tap on one end that we can close or open. And we fill this with a combination of liquid and organic phases. Often enough, the organic's going to sit on top, just like oil sits on top of the water. So we have an aqueous phase and an organic phase sitting inside of this piece of glass, right? So let's draw a more non-polar organic molecule. So something like that without really a dipole moment, that's going to be more soluble in the organic phase than it will be in the aqueous phase, and we'll be able to separate it out. So applications where we want to separate out things, there's a ton. The one that's kind of more near and dear to my heart maybe is thinking about coffee and how we're going to extract caffeine for decaffeination. So there's lots of organic non-polar solvents that have been used. We don't tend to use those anymore just because people get weirded out if we say that we've dissolved all of your coffee beans in hexane first, and probably for good reason. So we've gone in large part to just carbon dioxide, but supercritical carbon dioxide. So it's, even though it's a gas, it behaves like a liquid. And this is a non-polar molecule. So it's a non-polar solvent, and it solubilizes caffeine quite well. So if you wash out the beans with supercritical carbon dioxide, you take a lot of the caffeine out with you and leave a lot of the flavor behind. So it's kind of the best option we have for decaffeination. Okay, and that's just the quick note about different solvents and how they might apply to organic chemistry. So we'll stop it there, and I'll talk to you next time.